This is a short CV of myself, BSc in chemical engineering, and then actual production engineer during Iran-Iraq war for 4.5 years. And then went to UK, got a PhD in petroleum engineering, and I've been at Edith University as a staff from 1994. And then I formed Hydrafac Limited in 2006. And the area that I work is gas hydrate, flow assurance, PVT and phase behavior, production technology, petroleum engineering for other disciplines, gas hydrate, PVT, flow assurance, positive application. So that's my thing that I work on. And can you recognize me when I was a production engineer? That's me. That's me. Let's see. Okay. That's me working for Schellenberg. No, not for Iran, for oil industry in Iran. And Schellenberger was giving us some services. Here, I can cover a lot of area, but as a sort of, it really depends what you want, you know. Some area that, you know, I know that is necessary. Some area that you know that is necessary. So I very much hope that we work together to make a very useful course for the parents. So in introduction, I will cover how reservoir fluids are formed, where oil industry started, current trend and challenges, type of reservoir fluid. You know, when we say gas, we say wet gas, dry gas, gas condensate, oil, you know, volatile oil. How we find them. And then how we get access to them. And then drilling processes. Because drilling is a very expensive process. So we need to have a good chance of achieving the oil or gas. Seismic survey, well planning and site preparation, and then production system. When we call it primary, secondary, and tertiary, and then basic component of a production system, and what is the role of a production engineer? What we expect from a production engineer. Something that recently become very popular is unconventional reservoir. What are they? And then on the well completion concept, when you drill the well, you need to decide how to complete the bottom hole. how you bring it to surface, which component you want to have, which facility you need to have, and which component you use to achieve that purpose. Once you find good chance of drilling and finding a reservoir, you need to drill. In drilling, you have a conductor pipe, then you do 1858 casing, cemented. This is general, typical. 1338, then casing, and then 958 casing, and then cemented. And then most of the time we have a 7-inch liner. Obviously, different countries and the depths of the reservoir, they can be different. What we call it bottom hole completion is what is at the bottom here, bottom hole completion. And that can be normally open hole, pre-slotted casing, and then, but more conventional one is cemented and perforated. And then there are different versions of this. This can be horizontal, can be multilateral. Here you can have expandable screen. You can have, different techniques. And the next point is that how you bring the fluid to surface. And that depends on the cost, flow stability, control flow, and well safety. And that is production conduit, how we bring the oil or gas to surface. There are various techniques, but this is the most popular technique. Tubing flow with analog isolator. And that is, so this is tubing, flow in the tubing, and here packer to protect the casing. That is the most popular completion. And then the minimum requirement is that you have a perforation, you have a tubing isolator, and then analog isolation, that's the packer, and then a sliding side door, because you need a communication between tubing and analysts, if necessary, to open it. And then subsurface safety valve, and then surface isolation. So this is the minimum requirement. But it can be a lot more different other components. You can have downhole detachment, tubing stresses, because oil from reservoir is warm, so that will increase the length of tubing. If you are injecting water from surface, then that make the cold water and make it smaller. Then you should be able to manage these stresses. And then abilities to suspend uh, pressure and temperature equipment, control fluid injection, downhole pump system, and wireline entry guide. So that is the minimum, basically conventional, general. So from bottom here, wireline entry guide, nipper, perforated joint, nipple, packer, seal assembly, a sliding side door, and side pocket minder, subsurface safety valve, wellhead, and Christmas tree. We obviously we explain, depend on your area of interest. We can explain a lot more during the course. So these are stream components. So here you can see that when you drill, you put the first casing, and then drill the next one, put the second case, and then casing head, yeah, and drill the next casing, and then tubing head, you see that? And then here is bottom safety valve, bottom master valve, top master valve, and then injection valve and production valve, and another valve for vertical access to the reservoir, to well, and then the top pressure gauge. Now, this is wellhead. Up to here is called wellhead. This is called Christmas tree. And there are various techniques for completion. This one is for a single zone, and normally this is for a gas, because here you see that as the pressure, the gas comes to surface, volume increases, therefore area for flow will increase, therefore pressure drop would be less. This is another one with side pocket mandrel for injection of gas to help the oil. This is for oil reservoir, to help the oil to produce. We discuss all these components very in details. Or we need to have a pump, downhole pump. That's another possibility, which is becoming more popular. And then is multi-zone. So we are producing from the top zone, from this, and we produce from bottom zone, from here. Why we do that? Because of economy. And this is, as I mentioned, uh, compact wellhead, and this is Christmas tree. And it can be very complicated offshore. So we discuss all of these. If you are interested, we can discuss it. And multi-zone production, we can have commingled flow, segregated flow, or alternative flow. So we have more than one area or one depth of production. We can mix them together, when and why we mix them, and segregated them, design of the well, and alternative, how we produce. For example, here is dual zone, segregated zone. You see that the bottom zone produced from this tubing, and the top zone from this tubing. This is alternative zone. We produce from this zone for a while, closed side pocket mandrel, sliding side door, and then put a plug here after 6 months, open side sliding side door. We produce from this zone. Perforation. Perforation is the communication between well and reservoir. There are various techniques we can do that. And they are decided on shot density, number of shot per unit length, shot phasing at what angle they are. For example, this is 0 phasing. This is 180 phasing, 120 phasing, and 90 for direction. Normally, this is more popular one, but we can have 60 and 45. This is shot density of 4 shot density. Here is at 0 degrees. You see that? All the shots are in one direction. Or here is 90. One shot here, one shot here, one shot here, one shot to the here. We discuss what is the benefit of this one, what is the benefit of this one, or other area, other possibility. For example, one area of on horizontal well, if you have sandy reservoir, you inject all the shot to the vertical, because that form an arch that prevents sand production. Another area is a slick line or open hole and case hole logging. And that picture you saw was a wildland services by Schlumberger. And this is basically here, there is a truck here, and this is the wire. This is a stuffing box, and then this is what it's called lubricator. This is safety valve, and connected to vertical well. It is very clever design, and I learned a lot from them. And while I'm tourist string, we need to have ability to lower to well. We need a stem that is a heavy weight metal, and then knuckle joint. This is knuckle joint. Jaw. These are jaw, power jaw, and mechanical jaw. And then ability of here of different component of wide line here. And here is rope socket that connect all of this to a rope. And then different, equipment can be added to the bottom here, to do different measurement. Gauge cutter, impression tool, blind box, tubing, perforator, running and pulling tools, switch, wire and spear, bearer, positioning tool. There are a lot of equipment that we can add. The most interesting one is through tubing production logging, because like a doctor, you get some sickness, you need to do examination. You need to go to the doctor, and the wire line provide those information. Is like doctor telling you go to do this test or this laboratory. And these are some of equipment, temperature devices, bottom hole pressure devices, densitometer, flow meter, noise devices, cement evaluation, radioactive tracer and detector, pulse neuter, and gamma ray. So there are various devices that we can send from the top of the reservoir or well to gather information. So here, a typical casing current locator, thermometer, pressure, the shows that what is the available diameter available. The, in a way, densitometer, and at the bottom is flow rate measurement. This is like cement bond cement bond log. Cement is very important. Cement behind the casing is determine the fate of that reservoir. that well. So it's very important. Unfortunately, is ignored, and that causes a lot of safety issues. From this cement log, we can see that what is the quality of cement. For example, here, I can say here, good quality cement, yeah, and here is not very good. Here we don't have any cement. See that from the white section here. So we need to inject cement. Now, then we discuss about the basically theory of production from wells. The flow in reservoir is radial flow. So initially, when we produce, pressure drop near wellbore. With more production, the pressure in the well will be reduced and the flow, the pressure reaches the boundary of the reservoir. And then based on this, we can develop equation based on gas, oil, on gas and oil production. We will discuss all of these in details. So here, for oil production, this is Q, that is viscosity, formation volume factor, this is permeability, this is height of perforation, and this is the radius of well, this is the boundary. You see that all of these are fixed. The production for a single phase, liquid phase, is pressure difference. But normally, we don't have this. We have, that was one oil phase. Here we have multi-phase flow. Therefore, it is more complicated. So we need to work with a more complicated device, equation. Two-phase flow, there are various options, but the most popular one is Vogel equation. That follow this equation. We discuss, this is the most popular equation. We discuss with some example how it works. If the reservoir is above saturation point, in above saturation point is pressure difference, but here is Vogel below bubble point. And we need to build this equation if the reservoir is above its boundary, above bubble point, and then near boundary is two-phase. Gas reservoir is different. gas reservoir is pressure to power 2 for the boundary and flow at a constant and the power here. Then, so now with this equation that is single phase oil, single phase gas, multi-phase oil and gas. We calculate pressure drop from reservoir to well. From wellbore is tubing production. Now, tubing is friction if it is single phase. We can also calculate, this is pressure drop. Now, geothermal temperature gradient, it normally is 30 degrees per kilometer. And this is flowing temperature. So this is surface temperature of the oil. This is surface pressure of the oil. Therefore, you see that the oil will go through temperature and pressure differences from bottom hole to surface. So we need to identify which phases is the flow will go through. For example, for a gas condensate reservoir, what you normally can expect initially come into the wellbore as a single phase liquid, then bubble flow, and slug flow, annular flow, and mist flow. This you can assume single phase mist flow. You can assume this one, bubble flow, is mist flow. And this single flow is single phase. Okay? But they are not, these annular flow or the slug flow, they are not single flow. So therefore, that is very sophisticated test and equation developed to model this. In general, we can, delta P is delta P elevation to the depth of the well, friction, which follow Moody diagram, and then delta P because of acceleration. One thing that a lot of engineers do not basically take into account is holdup. We will discuss holdup. It is very important. We will discuss the importance of holdup because it has very important effect in pressure drop calculation and when to take sample. Because sample on the surface is much cheaper than bottom hole, although in some systems we cannot. So sometimes another option is using gradient curves. That we give some example on how to use gradient curves. Another problem is choke. What is the role of choke? That a lot of people do not follow what is the role of choke. They say that why you put such a strong resistance in flow. We will discuss it a lot. It is very important to understand when the flow is choke, when it is restriction. What is the maximum flow of a fluid or two-phase is across a choke. Choke basically separate production from reservoir. How we can accumulate several wells to one separator without choke? We cannot produce several wells to one separator or one header without choke. Because some of them, they are stronger, they have higher pressure, we not let production from other. So choke, the importance of choke, we will discuss. This is when a contractor, this is the process of flow across choke. For a gas well, the pressure downstream a choke should be half, at least half of upstream. We will discuss why. And then from nodal analysis, we can say that how much this well will produce. You see that? This is flow from reservoir. This is flow through tubing. That is the point of maximum production. Or, depending on choke size, we can decide that how much we produce. Another important topic is oil and gas processing. Oil and gas, when they are come to a choke, that was one well here, one well here, one well here, one well here, one here. Each of them can only come to one separator with choke. Without choke, they cannot produce. And then in the separator, we separate gas, oil, and water. Because oil needs to be stable at pipeline condition. So for a manifold, we have primary gas water separator, and then with different, here the oil reservoir, we had the field about in charge of unit 2 of Ahvaz. We had 4 separator for maximum oil production. You cannot do this in offshore. Offshore, because the space and weight are limitation. So normal offshore separation is 2 stage. But in onshore, you can have more operation. And this is a full production unit. You need high pressure, medium pressure, low pressure, and then water, oil separated from water here, or gas recovery, any oil recovered from gas phase, come back to the gas. The aim is to maximize the amount of liquid. That's the aim. Flow assurance, another key area. And hydrate, corrosion, wax, asphalting, skate, sand, other issue, emulsion, and other things. We discussed these and how we design them. For example, this is here, wax phase boundary here. This is hydrate phase boundary. This is asphalting phase boundary. This is onshore. This is offshore. So you need to have phase envelope. That is the importance of PVG. So we need to have phase envelope. This is the path reservoir fluid is taking, but you can change this. You need to have this information and hydrate phase boundary, wax, asphalting to choose which path to choose, and in future what will happen. In future, you can see that the pressure will drop. So you pass this way. So this is different salt calculation, scale calculation. So you need to have all this information. Sand control. Sand can cause serious damage. And here I was talking about horizontal perforation or vertical perforation. You see that? Here, in a horizontal well, you can have perforation upward and they form an arch, preventing sand production. Then intelligent well, a smart well. In fact, what it does, it will, for example, this case, we have 5 wells producing from 5 zones with different pressure and temperature. Conventionally, we follow this way. But now, smart wells, we can, with one well, we can achieve this. But obviously, it is more complicated. But it's possible. Plugging and abandonment. After a while production, we have to basically plug and save the leave the oil or reservoir oil well. Then there are different techniques to increase production recovery. We discussed these as well. advanced well, reducing pressure drop, wellbore, formation damage, acidizing and fracturing, tubing design, artificial lift. There are various options there. Formation damage, it is very important, especially near wellbore, because of increased gas saturation, reduced to permeability to oil, increase oil viscosity, increase the volume flow rate, because has a lot more volume than oil. Acidity is very important. For example, normally near wellbore, because of mud or different problem, has lower permeability than the main body of reservoir. We can do acidity or fracturing to solve this problem, but needs a proper modeling, proper study. Artificial lift, we discuss artificial lift, how they are important, how to choose which one. Rod pumps, electrical submersible pump, and gas lift. And artificial lift, basically you're providing extra energy to the oil. It can be with electrical submersible pump or gas lift. These are most popular ones. But there are other techniques as well. I was involved in a reservoir in Oman. They were using steam. And then the artificial lift they were using was producing a lot of sand. And we managed to change the artificial lift and have more oil production without less damage to reservoir. Basically, if you have a pump, you basically, the level of oil comes up to here. So it doesn't come to surface. Here with pump, we increase pressure. Now bring it to surface with a positive pressure. Therefore, produce more oil. In the beginning, you don't have any oil. So we discuss how they are designed, how they are operated. Another artificial lift is gas lift. And we discuss gas lift. And basically what it does, in gas lift, you have several gas offloading valves. These are valves. Then you decide one valve as operating. Normally, the lower is the better. Because with gas lift, you inject gas that will change the basically uh, pressure drop, because the density of the oil is reduced. Pressure drop due to density is density multiplied by height of the oil. So by changing the density, we can, instead of having a pressure here, pressure is 1000. But there is always an optimum gas lift, because the frictional pressure drop depend on the volume. Hydrostatic head depend on the density. The total pressure is both of them. So this is the total pressure. This is as low for gas lift, amount of gas injection, the pressure is high. You increase the amount of gas, hydrostatic head is reduced, the total pressure drop will reduce. But from here, the frictional pressure drop will increase. So maximum production is here. So we can design gas lift. Environmental impact is the very important and becoming more and more important. And obviously, we want to have minimum damage to the environment, and we can evaluate environmental impact. There are other areas that we can cover in addition to this area, depend on your interests. These are the areas that we can cover. Some of them we already covered, but it's up to you basically what you want to cover. I don't know, we can give you a copy of this or possible topic, and you can decide what we want us to cover. Thank you. Thank you very much.